Okay, so ladies and gentlemen, thank you for coming back to hear this presentation. In this talk, I want to introduce you the decision support system that we developed in our Guantao pilot. And I will also share some experience with you about the tools and the workflow that we used in the development. So I hope the talk will be helpful for your project in future. This presentation will be organized into 4 parts. So first, I will talk about some background regarding to the concept of this decision support system and the brief introduction about our decision support system for Guantao. Then I will make an online demonstration on my computer and to show you how it works and how it looks like. Then I will touch some technical details regarding to the tools for development and for the deployment. Then I will come with the final conclusion. So background, what is a decision support system? So by definition, the decision support system refers to the information system that helps decision maker to solve structured or semi-structured problem using data and models. So here I highlight 2 terms. One is information system and another verb helps, which I would like to spend a few more words on. So first, for the information system, nowadays it can be understood as a computer program. And as a computer programs, it can take form as either a local apps or apps that are installed on the server, which can be accessed online. And such web-based applications is becoming very popular nowadays as a solution for the modern software development, because any kind of smart device with browsers installed can using these kind of web-based applications, right? Now, another important factor is that for the decision support system, the goal is to provide suggestions to the decision makers rather than take over the entire decision-making process. So it accomplishes such goal by processing various information such as inputs, such as like, the paper form data or the measurement data or even satellite data. And then it will extract the refined outputs which are relevant to the decisions. Then the core component is this processor, or in other words, the models and the algorithms that translate such inputs into output. So here I want to show a routing problem as a simple example. In this example, we have a person who wants to reach this destination where the yellow flag locates. And then he or she needs some advice about the path to choose. So assuming our criterion for recommending such a path is based on the travel time being as short as possible. So to solve this problem, the first step is, of course, to collect all kind of information that might be relevant. For example, we have to enumerate all possible paths, and then the number of the traffic lights in each path that might hinder our travel time, and also the period of the busy hour that might cause traffic jam. Now, after the information collection, we have to formulate how we calculate such travel time. Do we simply divide the distance by average velocity, or should we consider like more comprehensive way by considering the variations in speed as well as the delay by any obstacles? So in any case, the final formulation that we design actually represents a model. And then with the data and the model being ready, we can easily estimate the travel time by simulating our model with different inputs for each possible path. And then the decision makers can use those estimates as reference to make his final decision, right? So from these examples, we see the 3 steps to solve a typical problem. And these steps are corresponding to 3 main components found in any decision support system, namely the data, the models, and then the decision support. And in particular, the data is the building block for obtaining good models. And then with proper models, one can deliver good decisions, suggestions to the decision makers. So in our project in China, our works actually encompasses each of these parts from data model and the decision support. Just to give you an overview, for the data collection, we collected electricity data as a proxy to obtain this groundwater pumping use using the electric to water conversion methods. You have seen this from the talk by Dr. Lu Wan. And also we collect some other conventional data like the heads observations, meteorological measurements, and also the hydrogeological data, and so etc. Those data are typically used for the calibration of the groundwater models. And based on this data, we developed a number of models. And for groundwater model alone, you have seen that we have this 2D numerical models using water flow. We have this 0D groundwater model using the water balance equation. And we also tried out this data-driven model based on the support factor machine learning technique. And we have this common filter-based real-time modeling approach. And apart from the groundwater model, you just heard this irrigation calculator, which implemented the FAO's methods to estimate the irrigation, the crops irrigation water demand for Guantao and for the North China Plain. And we also have the satellite-based algorithm to extract the crop maps for the main crops in our study region. And this is implemented in the app called the Crop Mapper. And you see, actually, those models even have their own interface that you have seen before. And then with those data and models, we propose a strategy for managing the groundwater in our study region by planning the amount of water that you can pump from the shallow aquifer and how much winter wheat crops that need to be fallowed in order to mitigate this overpumping. Since the winter wheat here is the main water consumers in Guantao. All these strategies are based on the concept of the groundwater red line, which I want to explain in details in the following slides. So the red line refers to an upper bound and a lower bound for shallow aquifer pumping. For the upper bound, the goal is to avoid the soil salinization issue due to the high groundwater level. So in Guantao, based on the hydrogeological data that we have, there is barely phreatic reverberation 5 meters below the ground. So we set this upper limit as the 5 meters below 5 meters depth as the upper bound. Then the lower limit for this red line is a little bit more sophisticated. We have two criterion. The first criterion we consider is the impact of the reduced pump yield due to the groundwater decline. So as you know, with the lower groundwater table, the distance for water to be lifted up by a pump will be larger compared with that under a higher groundwater table, right? So according to the energy balance, the decrease of the groundwater level will reduce the rate of pumping yield. It's like originally you can at best carry a 10-kilogram bag and climb a stair of 20 meters high. And now if you have a stair that is 30 meters high, you can only carry less, right? So in Guantao, a pump is also shared by multiple farmers. If the yield is decreasing too much, then farmers has to queuing up for a longer time in order to have their crop irrigated. And those people who wait at the end of the queue might miss the best irrigation timing and also spend more money on the energy costs, which is unfair. So in Guantao, we consider a 30% of reduction of the pumping yield with respect to the normal yield is a threshold. So more than that will be unacceptable. This is the first criterion. Then we have a second criterion, which we consider the groundwater's we consider a groundwater reserve for buffering extreme climates, such as multiple drought years. And in this kind of extreme climate, there will be sharp decline of the groundwater table. So we need to preserve a certain amount of aquifer storage for hedging such drought risk. And this amount of storage is translated into the equivalent changes of groundwater level, and then we added it up to the first criterion. So in the end, we obtain the final values for this lower limit, which is 30 meters below the ground in Guantao. Then with these two red lines, we can define a region where the shallow groundwater table shall be maintained. Then we can organize our quota planning. In Guantao, we suggest that such quota planning shall be carried out annually in each September, because in September, the 90% of the annual rainfall has occurred, which contributes a major recharge term in the water balance. And moreover, because the winter weed has not yet been planned in September, the local authority can further decide how much winter weed shall be fallowed in advance. And also there is this seasonal winter weed fallowing subsidy program undergoing in Guantao. So then these two can go hand in hand. And during the planning, we begin with the observed heads at current time step. Then we can specify the target head that we want to approach for the following September. And with both the initial head and the target head being defined, then the transition between the two states is mostly driven by the pumping and the recharge, which is described by our groundwater model. Then we can estimate the amount of groundwater pumping that corresponding to our target head. And this pumping quota can be further translated into the winter weed areas, which helps decision maker to determine how much winter weed that should be fallowed if necessary. And such quota planning is made possible thanks to the data and the models that we developed in our projects. So that's quite naturally that in the later period of our project, we decide to integrate the data and the tools within a single system. And more importantly, we want each component interact with each other in order to achieve the decision support. So now, before I show the decision support system that we developed for Guantao and make the demonstration, I want you to meet our target user, who are the staff from the local water resource bureau. So the main jobs are the water planning and the maintenance of the facility, as well as the fee collection. And these people do not have quite experience in using these professional tools like GIS software and the groundwater models, etc. And also these in these small counties, they are short of labor force, so they cannot allocate particular persons just to handling these technical tools and maintain it. And this is important when you need to design your decision support system for your client. So in our case, we co-designed our system with them, and then we followed these three criteria that I put it on the right. Those criteria, first is that the interface should be user-friendly. So we try to make the buttons as less as possible. Then the results should be conveyed in an intuitive way, so they can easily understand. The second criterion is the easy maintainability. So after the project is over, we want them to be capable of maintaining the software with the least labor and also the monies. So in this case, we consider our implementation using the open source software. So it means free. Then we use this modular design, so you can easily switch on and off some particular functions. And then it should be portable and scalable if they want to move this software to other platform or upscale it to a different region. And the last criterion is, of course, it should be useful to simplify their workflow. So, for example, the system should automate some data processing for them and also provide some assessment. And in the end, it should achieve the decision support. So overall, our goal is to simplify the user interface as much as possible, but still trying to have this system as capable as possible on the background. In the end, we implement this system as a web-based applications, so users can access it from the browser anywhere with internet connection. And all these heavy-duty computations for the models and the data analysis are done on a cloud server, which installs all the data and the models. So now let me show you how our decision support system look like and how to use it. This system is installed both in China and in Switzerland, but now I will use the Swiss one for demonstrations, and the address is this www.if-gwm.com. But you will have it anyway after the lecture, because we will pass you the slides, or you can send me the emails to ask it explicitly. The suggested browser for the best experience is one of these three. So either Chrome browser, Firefox, or Edge. Now let me switch to my screens on the browser and show how it works. So when you go to this website and open it, you will see the list of the applications that we made. This includes the data-driven model and the real-time model for demonstration, and you see yesterday already. And this one, the second one, Guantao DSS. This is the one that we implement for Guantao. So if you click, it will take 1 or 2 minutes to load the system. So just to be patient. So after you load these systems, the first page you see is this homepage. On the top panel of this homepage is the background regarding to this pilot region. And then on the lower panel is the a list of the description regarding to the modules that we implemented in this decision support system. And there are a number of them. For example, we have this water quota planning module, which helps the decision maker to schedule the amount of shallow water pumping for the next year, and also for the winter wheat fallowing area. We have the scenario analysis module, which actually includes 2 groundwater models, and then you can use these groundwater models to do some scenario analysis and to refine your management strategy. Then we have this crop water demand module based on the irrigation calculator for calculating the crop water demand. And also it includes the numbers from the official document as a comparison. Then we have this crop mapper that implements the visualization panels for this satellite-based algorithm. And then one can load the results processed by this crop map app and show different the spatial distribution for the main crops in Guantao. Then we have the final data portal module, which is the modules that you can either download the data or you can visualize all this data that we stored in our database. So now let's just go over each modules one by one, starting from this water quota planning module. Let's click there, go to the module. So under this quota planning modules, you have actually 2 parts. The first part is the overview of the current status. Then in this part, the idea is that the users can quickly have a glance of the numbers and the pictures and understand what is the current status. And in this map, you see this spatial distribution of the depth to groundwater model, which is output of our real-time groundwater model. Different color has different meanings. So the red means the depth to groundwater table is higher than 30 meters. So the groundwater head is really low. And then the green means it's high. In some cases, if it's too low, then we have even the warning message showing up, indicating, for example, in Shoushan Township, the groundwater table is too low, so pay attention to that. Then beside it, on the right side of this map, we have a number of statistical indicators, starting from the average depth to groundwater tables measured in recent September. And for example, in this case, for September 2019, the average depth is 22.3. Then we also have the water use statistics for different water source. So how much water is used for surface water and for the shallow groundwater pumping and deep groundwater pumping. These figures are interactive, so you can use your mouse, try to click or drag it and see what will happen. And this is another indicators based on the normal, based on the historical observations. Besides of these simple indicators, we also implement a few other indicators according to the request of our decision maker. So in this case, we have the reference status, and then we have the indicators for groundwater use, surface water use, average depths, annual precipitation, irrigation area, and the winter weed areas. And to facilitate the comprehension, we use this color coding. So different color actually already give you the information of how good it is. The blue means the situation is more or less the same as the previous year, so which is 2018 versus 2019 as a reference. The red means it's getting worse. Then the green means it's getting better. So quickly, by looking at the color and the numbers, decision maker can have the brief understanding of the current status already. And then apart from this overview panels, the most important part is this design my plan. So in this part is where the decision maker can achieve the planning for the shallow groundwater pumping. In this case, we only give them two options. So it's really simple. First option, the first input option is the target depth to groundwater table. Then the second option is expected surface water supply. And using these sliders, you can just change the values accordingly. And then these values will be memorized by the system. And then once you click the start planning, it will execute the planning modules to give you the suggestions, which will be shown below. But even though these options are very simplified, there are a lot of things that are undergoing on the background. For example, this feasible range for the target depth is calculated automatically based on our groundwater redline concept, and it's 5 to 30 meters, as I mentioned before. So now let me show you how the suggestion is generated. For example, we put the target depth to 18, so which means we want to bring the groundwater table 4 meters higher compared to this reference. Then we click start planning. Then the results is showing here, telling you that even with zero pumping, the target cannot be reached because this is too ambitious for the recovery of the groundwater table within 1 year. And then the suggestion is that either increase the surface water supply or the target depth. So for example, if we make it a little bit less ambitious, so to 20, so we recover only 2 meters, and then we click start planning again. Now there's new plans displayed under this part. And the results showing you that so much amount of water can be pumped from the shallow aquifer. And then the corresponding winter wheat planting area is at most so much mu. So mu is the area unit in China. And then the corresponding fallowing area will be so much. So with those numbers, the decision makers can already have the brief ideas of what they should do for the following years. And then based on these rough planning numbers, he can further adjust it using our scenario analysis module. And as I mentioned before, the scenario analysis module includes 2 groundwater models. So the first groundwater model is this box model from Dr. Luan. So in this box model interface, you have the input part on the left, then you have the output part on the right. And for the input option that we included, we have the total electricity use, which will be converted to the groundwater, to the water use using the electric to water conversion methods and all the parameters that we calibrated based on the field experiments. And then the second option is the expected surface water supply. And also, if you want to see what is the corresponding water use under the given total electricity use, you just activate this radio button, and then you will see the corresponding amount of pumpings from the groundwater and also for the surface water. These values will change automatically when you change this electricity use. And then after you decide all these inputs, you click calculate and write. Just take a few seconds, the results will be shown on the right. And on this right panels, the blue lines show the historical observations. And then you will have the forecast depth to groundwater level for the 2020. So for the following year. And this is shown as a triangular region because it considers an uncertainty due to the hydroclimatic variabilities. And the default results is shown in normal year. You can also try to switch to the dry year and the wet year, and you can see what could happen. These figures are totally interactive, so you can put your mouse to inspect the values in detail. You can also zoom in to a particular time period in order to have a more detailed glance, or you can zoom out. And you can also download the full-fledged version implemented by Dr. Luan by clicking this download box model. Now, the advantage of this box model is that it's very easy to use, so it computes very fast, and the result is very intuitive, but it does not give you the information regarding to the heterogeneity of the groundwater head over the space, right? So to conquer this weakness, we have this distributed model, which is implementing the numerical models implemented by our colleague, Dr. Ning Li. So in this 2D model panels, you have the inputs here, and then again, you have the outputs on the right. And because it's this is distributed one, and it's more comprehensive, you have more inputs as well. For example, you can define your boundary condition for the annual rainfall. And you can also specify the surface water supply. And in addition, you can define the water allocation setting at a township levels, instead of having the water use on as a box. So in this case, you can change the crop water demand. So if you click this gear icons, then this window will pop out. The default value for the different main crops in Guantao is calculated automatically by our crop models, as you see in this irrigation calculator. So actually, we already coupled these crop models with this groundwater models in this case. Then you can further modify the reference values just by dragging these sliders. Once you decided the inputs, just click OK, and then the inputs will be saved in the system. Then there's also the options for changing the allocation setting per township. And we have 8 townships in Guantao. Now the one that is showing here is called Luqiaoxiang, which is highlighted in these green patches. You can change the township by choosing it from this drop-down button. So for example, we can switch to another township called the Shoushansi, which is here. And under each township, you can further modify the irrigation area per each crop. You can also change the total water use as well as the surface water use with respect to the surface water use ratio with respect to the total water use. And at the bottom, you have an additional buttons that you can activate. And it allows you to add recharge points into our pilot region and see how it can help to mitigate the groundwater overpumping. To use it, you just click, then there's another input option pops up, telling you what is the number of days for the recharging. And each recharge point occupies a land of 40,000 square meters based on our field experiments during the project. So now without changing anything, let's use the default value and then we see what would happen. So we just click this calculator, and now there's this progressing bar telling you that the model flow model is being executed. Actually, it's very fast. So now you have the results, which is a map overlaid on this space map. So different colors tell you the level of changes. And this results is for the end of 10 simulation year. So this numerical model we implemented as a transient model, and it's running on the annual time step for 10 years. The default is the 10th year, but you can also change into the first year, which you see this kind of red coins is still small, and then gradually it expands. And at the 10th, the final time step, it is stabilized into this kind of situations. If you want to extract the change of the water level time series at a particular location, just click at a certain point. Then you see this marker here indicating that this is a location that you select. And then the corresponding time series for this 10-year simulation will be shown at the bottom. And for different allocation settings, you can also have overall glance. Whenever you change the allocation plans, the results will be shown as these bar plots. So with this numerical models, we can see the spatial distribution of the groundwater head. And we see there are two places where the change of the decrease of the groundwater level is quite significant. One is here and one is here. And you can use this input options, try to implement some management strategy. So let's start from this region, which is actually 受3.4. So let's go to here. Then we can see what we can do in this case. So one way to do it is that we can reduce the total water use. You can either change this slider directly, or you can change the irrigation areas from these buttons. So for example, let's cut the winter wheat area into 0. And if you click OK, you will see that the total water use will be updated automatically, because this will be computed based on the crop water demand and also the crop areas. And then once you decide the input value, for example, we also increase the surface irrigation ratio a little bit, then you can click calculator. Now with the new settings, we execute the groundwater model again, and then we can try to observe what might happen in these situations. So with the new allocation setting, we see this red patch is already gone. So we achieved the mitigations for the 受3.4 regions. And we still have these patches on the north. So let's try another approach by building some recharge points. To do this, as I said before, we activate this radio button. And then to build the recharge points virtually, you just put your mouse in the location where you want to have this recharge points and click. Now each click will put these droplet icons to indicating one recharge point. You can click multiple one, but you cannot have more than a certain amount, because all these recharge points, the water comes from the surface water, and there is some limits. For example, here it says you cannot build more than 4, so it tells you the error, and then you have to try it again. So let's have 3. Then we run the calculation again. Now we see that originally there is some deep red little patches, and with 3 recharge points, we can mitigate these very low groundwater level regions, but still you have a larger patches still persisting. So you can playing with these modules and trying out different methods until you see satisfied results. Apart from these groundwater models, we also have this irrigation calculator. This is the same implementation as the one that you've seen in the last talk by Dr. Bea, except that in this case, we tailored this irrigation calculator for our for our decision makers in Guantao. So some options is gone, so you cannot specify your meteorological inputs. You cannot change the irrigation methods, because we want to have it very easy to use by our decision makers. So it's less flexible, but the computational routine is the same as the full-fledged irrigation calculators. And again, on the left side is the input panels. You can change different plant category, and under each category, you can change different crop type. You can change the soil type as well, and then you can also change the planting date. Let's try with the winter wheat, and first September as the planting date. Then we run the calculation again, and then the results will be displayed here. So the results includes the monthly crop irrigation deficit and the wet, normal, and dry years. And also you have the annual water deficit for different weather conditions. Now, in addition to this irrigation calculator, we have another tab called irrigation norm. In this tab, we actually implement the documents, which was also shown by Dr. Bea. So we have this official document called the Norm of Water Intake in Hebei Province. On this document, they specify the irrigation norm for different crop types, and also they propose some kind of empirical formulation to adjust these norms, considering the water resource, the type of the water resource, the size of irrigation area, and etc. So we digitalize these documents into our system. And then with these panels, the users can easily look up these documents by just specifying the inputs, and then all the calculation will be done automatically. So they do not need to apply the formula themselves. Everything is already here. Then they can check the norms from that document and compare these norms with our values estimated from the irrigation calculator. And remember, the irrigation calculator is validated on the annual basis, so it's quite accurate with respect to that document. But the advantage of having the irrigation calculator is that you have the monthly values for the crop water deficit. Now, apart from these modeling tools, we have two additional modules for the monitoring purposes. The first one is this crop mapping. So under the crop mapping, this one is coupling with the crop map algorithm. So it will extract the processed remote sensing image, which is generated by this crop mapping algorithm implemented by Dr. Sylvan. So you can choose different crops, and then you can also choose different years, and then the results will be, let's say, input into this in this map. For example, let's say the winter wheat. Then we want to see the maps for 2019, and then we click load map, and when we click these load map buttons, it will start updating these maps by getting the results from the crop mapper and put it here. This map is in high resolution, so it will take a few minutes. So during the waiting time, let's have a look at this another output at the bottom. So in this panels, we have the time series for the crop areas and per each township. And if you want to focus on certain township, you just click this legend to turn it off. And then only the legend that is still alive will be shown here. Okay, and here now we have the result has been loaded. So in this map, we see the crops, the winter crop, which is represented by these green patches. Then you can zoom in and zoom out to have a clear view. And this is very useful because in this case, the decision maker can sit in the office and have just look at this winter wheat crops. Then for some regions that there are farmers who applied for the seasonal fallowing of the winter wheat, then he can quickly identify that some region that is suspicious. For example, there are farmers who applied for the winter wheat, but you still see the winter wheat here. So he can mark those suspicious regions by activating this add marker option and then click. Then each marker will tell you the coordinate of each point. And then you can add those points if you found it suspicious. And later on, you can use these coordinates to make a field visit to add to, let's say, to make a more official investigations. In this way, it saves a lot of labor forces for our decision maker. Now we have a look at the last panel, which is the data portal. So in this data portals, we can download the data. So the data that are stored in our database includes the meteorological data, the energy use, the irrigation area, the water supply, and the groundwater levels. You can also download the data to your local computer for further analysis. But here, because of the confidential issues, I do not put the download buttons for this workshop. But in our official versions, there is actually more options that the decision maker can get the data locally. Now, apart from this data archive option, we can also visualize the time series for different type of the observation data. So we start from this meteorological one. So in Guantao, we have one meteorological gauge station. The ID is this 54809. Then if you click this marker, it will extract these time series plots on the lower button. So you can, again, zoom in and zoom out to have a further inspection. You can also go to the groundwater levels. So in our case, we spend a lot of efforts to get these groundwater level measurements. And these measurement data are provided by different providers. So we have 4 providers. And if you want, you can just unselect some providers. So only the ones that are stay alive will be shown on the map. And the markers tell you the location of these monitoring wells. And there are the monitoring wells for the deep wells and also the shallow wells. If you click on the marker, then the corresponding results will be extracted here. And in some cases, you see a number because this monitoring well is very dense. So it's clustering together. You have to zoom in order to get it right. So for example, we zoom in, here is 4, there are another 4 monitoring wells here. There are another 3 monitoring wells here. You have to further zoom in. And some wells are multi-layered. So for example, in this case, it's 2-layered monitoring wells. And you can directly read it from this panel. The last one is the irrigation water use converted from the electricity. So again, you can read this time series for the water use from surface water, shallow groundwater, and the deep groundwater. And if you are interested in our partners website, and also if you are interested in this groundwater game, which I'm going to talk about tomorrow, you can go to this other panels, and if you click the image, it will bring you to the corresponding website. So with that, let's so that is a demonstration. Let's come back to the slides again. So far, we have seen how our Guantao DSS look like and how to use it. And behind those things is the integration of the different modeling tools, which makes the entire system functional. It all begins with this SQL database, which stores all kinds of data that are produced or collected in our project. Then we have seen different modeling tools and the data portals. The database will feed respective inputs into each modeling tools when it is in active use. For example, for the 0D groundwater models, it will extract the historical observation for precipitation and surfacing flow. And also we have some automatic process that is undergoing on the background, such as this data assimilation procedure. So whenever there is new data come in, this data assimilation procedure will be triggered periodically in order to keep our groundwater model up to date. And in summary, part of this module serve the purpose for quota planning, and part of the modules are used for the monitoring. Now, in the following slides, I want to talk about some technical details regarding to the development and the deployment of such DSS. The reason why I want to bring this topic out because the entire system, this entire system is implemented by myself with the contribution of models from our team members. So none of us are software engineers, nor do we hire any software companies to do it for us. Everything is done by ourselves. So that means the tools and workflow that are used in our project might also apply for the researchers like you guys in order to achieve a nice and functioning decision support system. So first of all, the entire system is built based on the programming language called R, which I think you might heard of. Nowadays, I think many of you heard that Python is very popular programming language, which is true, but actually R is widely used in academic fields such as statistical data analysis and modeling. You know, the Dr. Ning's data-driven model is actually implemented in R. The features of this R language is that first, it's free and open source, so it's free to use, and it supports multiple platforms. So whatever it's a Windows system or Mac OS system or Linux, you can download this R software. And this is very intuitive language, so it's very easy to learn. And this language has developed, I think, for about 40 years already. So there are large community package support. So you don't even need to implement the algorithms or models yourself. Like, for example, AquaCrop, you can have the R version that is already there, made by the others. You just take it, put your parameters for your case study and use it immediately. And among all these packages, we choose a specific package called Shiny, which is a package for developing the web-based application in R language. So it's natively supporting R. And also this package supports the development of the front end and the back end of the web-based application. And it is very easy to extend it if you know the programming language for the web development, such as CSS or JavaScript. So you can make the application better if you know more, but if you don't know it, it's still okay, because everything incorporated in this package can already make a very nice web-based applications. So I will not explain step by step how to make a Shiny applications. If you are interested in it, the official documentation will be a good start because it comes with good tutorials. In the next slide, I will just show you some general file structure for the Shiny application. So as I mentioned before, this Shiny application includes both the front end and the back end. The front end means the design of the interface, including the colors, layouts, buttons, etc. All the codes regarding to this front end design elements has to be written in a file called UI.r. Then the back-end development means how to make the response to the user inputs on the website. For example, if the user click a button, how should we execute a model and how to extract the outputs for display? Those implementation of the responses has to be coded in another file called server.r. So a complete Shiny application must contain both UI.r and server.r, and these are the minimum requirements. Then you can include other materials used by your application. For example, in our case, we coupled the original model flow executable files within our Shiny applications to build this scenario analysis module. Now let's talk about the deployment. The software deployment means installing the software somewhere for the access of the users. But unlike the way that we use to install the software on our own PC, a web-based application needs to be installed on a server. And the server is nothing but a high-performance computer that can be accessed on the internet all time long. When we visit a website, we actually, visiting pages or files that are stored on this server. But in order to get your application running on a server, we not only need to transfer all these files for our program to the server, but we also have to make sure the running environment is consistent with the one that you used to develop your applications. So that means the operation platform should be similar, or the dependent programs are also installed on the server, and etc. And these are quite some burdens for the researchers who do not have this experience in server operation. In our case, we came up with a solution by using a virtualization software called Docker, which is very popular in recent years. With Docker, you can package your Shiny application files together with its running environment into a single image file. Then you can transfer these image files to any server which has Docker installed, and then get your application running on the internet in no time. For example, in China, we set up these applications on Ali Cloud just in less than 1 hour. For details, you can refer to this paper that we published recently, which we will explain the mechanisms, and also we have some examples. Such development framework can be applied in a number of scenarios. The first scenario is for the small to medium project where a research team wants to upgrade their modeling tools into a decision support system by themselves and have it ready for use on the internet as fast as possible, like our cases. And if you have a big project where you can hire a software company to develop a decision support system for you, then our approach is also useful for prototyping the decision support system at early stage. So you can better communicate with the company about the function that you would like to have. Also, you can use these prototypes to communicate with your stakeholders, get their feedback, and improve the design of your system more efficiently. Then the last case for this development framework is to use for the teachings. As I said before, the R language is very easy to learn. So by teaching the decision support system, you can teach the students to integrate the data analysis the modeling, and also the decision support. So they can put the knowledge into practice. So all of those tools and examples are available on our online repository on GitHub. So you are welcome to download them and try out yourselves. So with that, I will come with the final conclusions. So in our case, the decision support system is a good way to integrate the technical products that we have during the project. And this system is co-designed with our decision makers, bearing in mind their characteristics and their background. Then all this software infrastructure is based on the open source tools. It's using the high interactive figures, and it's web-based applications that allows the further enhancement, and also can be used for the educational purposes. And our development framework is very cost-effective for the research teams who does not have much knowledge regarding to the software engineers, and it can be outscaled to other areas. So finally, I want to thank our team members who contribute their model and the tools so we can make this entire system possible. And with that, I would like to conclude my presentation and thank you for your attention. So I will be happy to take any questions for now.